bunch of clear granules that we use to make our food taste better. Well, that's certainly true of table salt, sodium chloride.
But did you know that salt actually refers to a very large family of compounds, many with quite different properties and uses to table salt? Let's start with what a salt is. It's an ionic compound made up of one or more positively charged cations and negatively charged anions. An ionic compound is electrically neutral. Watch this video if you'd like a refresher on this concept. The cation tends to be a metal, and in many common examples is one from group 1 or 2 of the periodic table. The anion is commonly a halide from group 7 or a member of group 6. Salts made like this are called inorganic salts, but this is not always the case. The ions can be polyatomic, that is, made up of more than one atom. A common example of this would be ammonium salts. You might wonder if all salts are small transparent crystals, just like table salt. Certainly not. Salts come in many different colours. Sodium chromate is yellow, potassium permanganate is purple, and iron disulfide is shiny and metallic. In fact, it's a mineral commonly called fool's gold. Another common mistake is to think that all salts taste, well, salty. Again, this is wrong. Some taste bitter, and some even taste sweet, like lead diacetate. Unfortunately, it's also poisonous. Here's another more complicated salt with nitrogen in the cation. It's part of a family called the diazonium salts, which are all brightly coloured. Can you think what they might be used for? Pause and have a think, then resume. The answer is they're used for dye pigments to colour our clothes. If you ever get the chance to enjoy some fireworks, the bright colours you can see are produced by burning the salts of various metals. You might recall learning that an acid plus a base gives you a salt and water, and that's quite right for an inorganic salt. Here's the classic reaction for making sodium chloride. Hydrochloric acid plus sodium hydroxide equals sodium chloride and water. Here's the thing though, hydrochloric acid, sodium hydroxide and sodium chloride are all water soluble and dissolve to form clear solutions. So the challenge is, can you think how you would monitor this reaction to make sure it is actually happening? Pause and have a think, then resume. Here's the answer. You would monitor the pH of the solution while you add the base gradually to the acid by titration. You could use an indicator like methyl orange. It's an orangey red colour in acidic solutions but turns yellow when they are turned basic. The pH would start at around 1 to 2, but as the acid is neutralised and the salt and water formed, it would start to rise. Once neutralised, the final step is to evaporate the water, leaving the salt crystals behind on the sides of your reaction vessel. Now, while this technique is good to know, we wouldn't ever have to create table salt this way in industry because nature does the chemistry for us, and sodium chloride can either be mined from the ground or evaporated from seawater. And don't think this is the only way of making salts either. They can also be formed by introducing a metal to an acid, as in this reaction, or by combining a metal and a non-metal, like a halogen, as in this reaction. All of these salts are soluble in water, but some salts are highly insoluble, and some are what we call sparingly soluble, meaning only a small amount can dissolve and the rest stays as crystals. Salts made with sodium, potassium and ammonium cations, and those made with nitrate anions are all water soluble. But most salts made with carbonate anions are water insoluble. Salts dissolved in solution have an important property, the ability to conduct electricity, and we call them electrolytes.